Yes. So it's fine now. Okay. Now, I want to remind you about what we have covered. So this is a reminder. We have covered what is called arithmetic sequence. I've given you the formula for arithmetic sequence. So it's T sub n, which is equal to A plus into n minus 1 multiplied by D. Tn is the nth term or the last term. Some they usually call it the last term of the sequence. And then A is the first term, n is the number of terms, and then D is the common difference. So you must not forget this, it's very important. And then number 2, what we have covered is geometric. I'm just reminding you so that when I introduce the new stuff for today, we don't have any problem. So the second aspect we have covered now is what is called geometric sequence, of which is given by the formula Tn equal to A first term r to the power of n minus 1. A is the first term, R is the common difference, N is the number of terms. Common difference is given, common ratio is given by T2 over T1 or T3 over T2. Similar with the common difference, which is given by T2 minus T1 or T3 minus T2. Don't forget these formulas, they're important. So this is for arithmetic and this is for geometry. Number 3, we have covered what is called arithmetic series. What is arithmetic series? So arithmetic series is given by the formula Sn, which is equal to n over 2 into 2a plus into n minus 1 multiplied by d. I've even given you the derivation for this formula because it's important for you to know the derivation. It might come in your exam. So you must remember that derivation where Sn it stands for the summation or the sum of the sequence or the series. So this is the formula for arithmetic series. And then number 4 is what is called geometric. So this is a geometric series. So what is a geometric series? So a geometric series is a series given by a formula Sn equal to A into r to the power of n minus 1, all divided by r minus 1. Or, okay, this is when r is greater than 1, but r must not be equal to 0. And then the other formula is Sn, which is equal to A into 1 minus r to the power of n, all divided by 1 minus r, or where r must be less than 1, but r must not be equal to what? 0. These are the conditions which you must remember. We have covered this already. Let me check. Okay. It's the formula zote zenda zimwareka bodo uko zibuwana ti. Hello, Kate. Kate. Hello.
Ndiko zibona.
Okay, yes. So these are geometric and arithmetic sequence and series. So you must not forget these formulas. So now, namusi ndiko yoku extenda a formula ya geometric series uri rikono kuishimisa musi rina number of terms ziko approaching infinite. Let's say we have infinity number of terms. So Sn is what is infinity. So what formula we have here if it's approaching infinity? So now this is what is going to happen. for this situation where R is less than 1. For example, if R is less than 1, need examples are R equaling 0.5. 0.5 rise square 1 again. We're gonna play 0.25, and then right cube root 0.5 to the power 3. In a plural again is 0. What? I don't calculate. What is 0.5 to the power 3?
Ah,
0.5 to the power 3. In a plural again 0.5 to the power 3.
okay. Irina ya 0.125.
0.15. Okay. Now,
125.
1 minute.
125.
125. Yes, exactly. So this is so now, as a 0 here, upper R equaling 0.5. But now R squared 0.5 squared getting there 0.25. Okay. Let me, this other person was joining just now. Okay. Now I was still explaining. It seems as most of you today are having network connection, but that doesn't matter. We are having the recording. So you will get a recording if you are not able to connect today. So I was explaining that today we have covered, we are going to cover the aspect under the geometric series, but that needs you to know some of the stuff we have covered already. So we have covered arithmetic sequence, geometric sequence, arithmetic series, geometric series. So today, our lesson focus is on covering the aspect when n approaches infinity. So I want to explain more about that because it's very important formula that you're going to develop there, where summation of the geometric series is approaching infinity. So let's check how that goes. Indeed, if n is approaching infinity, the first equation for geometric series is not going to converge. So it will be diverging, and that will not give us any information we're looking for. So, but now, if R is less than 1, if R is less than 1, it means the sequence is going to be converging in that case. In other words, we are saying that if R is less than 1, as an example, R is equal to 0.5. When we square the R, the value of R will be reducing, like what we have here. We squared 0.5, it's going to give us a value of 0.25. And then we cube root the value of common ratio there, you will see the value is going to be reducing in that case. So that simply tells us that when m is approaching infinity, something is going to happen on this value of r to the power of n. So the value of r to the power of n will be approaching what? Is approaching 0. That is very, very important, which we must take note of. Let me emphasize this again, because it's a very important point to take note of, that when the value of n is increasing, the value of r to the power of n is approaching a 0. It will be decreasing until it reaches the value of 0, even though 0 is an asymptote, but it will be decreasing to approach a value of 0. That's why we developed a third formula of geometric series, which we are going to have there. So the new formula for geometric series, which we are going to develop by using that theorem, is going to be A into 1, then where we have r to the power of n, we're going to substitute by the value of what? Of 0, because r to the power of n is approaching what? It's approaching 0. Take note of this, it's very important. And then now we divide this by 1 minus what? Minus r. Let's simplify and see what we get, which is going to be our new formula. 1 minus 0 is 1. 1 multiplied by a is going to be a, which is the first term, divided by 1 minus I. That is the third formula we're supposed to use. Remember, this is the first formula for a geometric series. And then now we have derived the third formula for a geometric series, of which you must not forget because it's important. Are we all together up to so far before we go to the other aspect of the series? So this is one part of the series we have covered up to that point, but I'm going to add another one before we go to the questions. So I would like to find out from you if you have understood what we have covered up to so far. Are we all together? Are we all together?
Yes.
Okay, wonderful. Let me go to the third aspect I want to cover with you under the series. So this, which I'm going to add now, it is a topic which is under arithmetic series, and it also applies when we have geometric series. So it's what is called the sigma notation. If you remember the last time, we have covered a series of which you can determine the series given by a sequence like that. So this is a simple example of a series, and you can distinguish that indeed this is a series, not a sequence, because we are having addition, or you may also have a subtraction sign in between. So, but this which we have there is what is called a series. So, but now we are going to introduce the aspect of sigma and notation on the series. So how can we write this series in terms of sigma notation? Because sigma notation is used to summarize the series that we have up there. Instead of writing many numbers that represent the series, you can then use the sigma notation to help you generalize the series you are given in that case. So now let's see how we can implement the sigma notation on the series. So now the sigma notation, or the general form of the sigma notation that represent the series, is given by this sign, which is called the sigma. So now this is the initial term, or the starting point, which in this case is I equal to 1. In some cases, it could be I equal to 0, which means the starting point is going to be from 0. But in this case, let's use the starting point as 1 up to n. This is the end point of that. Let me repeat this because it's important. That the sigma notation is given by the symbol we have there, and what we have below the sigma notation, it represents the starting point of the sequence, and this is the end point of the sequence. And then inside here, you write the general term of the series, of which we're gonna do that general term of the series using the example we have up there. So, but in the meantime, let's just find the sigma notation, the general sigma notation that you can implement in any kind of questions. So now let's expand this sigma notation so that you see how we attend to such kind of questions. Because we are starting from I equal to 1, okay, you can see in this case I used I, therefore even there you must also have an I because they must be exactly the same thing, but there at the end term you need to have the N. So now you substitute 1 where we have I is going to be term 1, which we know term 1 in this case is what? It's 1, and then plus. Indeed, because it's a sigma notation, you need to use the addition sign throughout, because this simply tells you that you are summing up all the terms you will be given. So this sigma notation, it tells us that you are summing from 1 up to n. Therefore, it's going to be T1 plus T2 plus T3 plus T4 up to the Tn, of which you cannot be able to write them. you cannot be able to write all of them in the board. Therefore, you can summarize by having the dots and then the last 10. So this which we have there is exactly the same as that, but now we have summarized what we have there by using the what? The sigma notation. So I believe we are all together there. Of which, let me do an example of the series we have up there so that you can see how we can represent the series in terms of the sigma notation. Let's do this example and see how we can represent this series in terms of the sigma notation. We're having a series of 1 plus 2 plus 3 plus 4 plus 5 and then dot 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 up to infinity. So the very first thing you can do from this is to get what is called the common difference, of which I believe you are all familiar with because we have covered that aspect already. So you can get the common difference or the common ratio depending on the kind of sequence or the series you are given. So here we can use the common difference because you can see the common ratio cannot work in that case. So the common difference is going to be 2 minus 1, which is 1. 3 minus 2, which is 1. I believe you can see that in this case we're having the same number of which justify or of which confirms that what we are dealing with is arithmetic series. So otherwise, if we did not get the same number here, we're not going to be able to confirm that what we are dealing with is arithmetic series. Okay, then after having that, you can then use the formula for the arithmetic sequence because you can see here we're looking for Tn, not Sn. Don't use the formula for summation in this case because it's not going to give you the answer. Here we're looking for Tn, of which is the arithmetic sequence formula. So it is Tn equal to A plus into n minus 1 multiplied by d. And then now we substitute the information we're given. The first term here we're given as 1 plus the n. We don't substitute anything for now. And then where we have d, we substitute the common difference we obtained there, which is 1. Therefore, now we simplify, it's going to give us 1 plus n minus 1, of which gives us an answer of n. That simply tells us that the Tn in this case is equal to 1. Let's substitute to the sigma notation if we want to represent this series in terms of the sigma notation. So our sigma notation is going to be sigma of, now you can see we're using the n here, not the I, we're using the m. Therefore, it's going to be n from what? From 1. It's not starting from 0 because if you substitute 0, you're not going to get the first term there. Therefore, it's starting from 1. What is the last term there? The last term, let's use n. You can't use n because n is already representing the number of what? Of terms. You can either use the capital letter or a different letter. Let's use the capital letter n to represent the last term of the series. And then inside here, you then write the general term of the series. And that will be what is called the sigma notation of this series that we have. So you can represent this series in terms of the sigma notation. Let me find out from you if you understood the two aspects we have covered here. I haven't done any examples that we're supposed to cover today. I've just introduced two important stuff today. The first is the infinite series of the geometric series. And then the second, I've introduced what is called the what? The sigma notation. Now it's your time to ask me any questions if you have any.
Ayo ene iri phanḓa ha sigma notation yo ṅwalwa sa final answer kana ndi mulayo uri i vhewe?
Yeah, this is the final answer. The n we write here is the n for the what? For the general term. You see, general term in this case is equal to what? It's equal to n. Therefore, here where we have sigma notation or where we have Tn, we replace by what? By the n, because Tn is equal to n. Yes. Okay. Any question before we go any further?
No.
You are fine, eh?
Yeah.
Okay. Let's go straight to the questions so that you see how we attempt to the questions that requires you to apply what we have covered today. Okay, this is the first question. It says, find the sum of each of the following. Infinite geometric series. Okay, this is the question. Now let's check what you are given. Let me start with this one for a series. Okay. That is the question we have on the board. That is the question we have on the board. Now, let me summarize the question for you so that you don't see as we are having a difficult question. It's not difficult. So now, let me explain to you what we have. So the question requires us to find the sum. Whenever we are talking about the sum, there's only, let me say, 34 formulas which must come into your mind. One formula, it comes from arithmetic series. I believe you remember the formula from arithmetic series. And then the three other formulas, they come from geometric series, of which I've introduced you. But let me summarize them quickly so that you don't go to the questions without knowing what you are talking about. The first formula is for the arithmetic series, of which is this one. I believe you know the formula by heart now. And then the second formula, it comes from geometric series, which is given by a into r to the power of n minus 1 divided by r minus 1. This we use when r is greater than 1. And then the other one is Sn equal to a into 1 minus r to the power of n, all divided by 1 minus r, where r must be what? Less than 1. Do you see the difference between the two formulas? Yes, you just swap the positions, né? So, because we want to avoid a situation wherein a denominator is negative. That's why we need to put this condition. The last formula is this one for sum to infinity is equal to a divided by 1 minus r. These are the formulas which must come into your mind whenever we are talking about the what? The sum. Are we all together?
Yes.
Okay, wonderful. So now, in this question, we want to find the sum of each of the following infinity geometric series. Already that statement is giving you the answer of what we are looking for. We are looking for the infinity geometric series. There's only one formula which talks about the infinity summation here. Which one talks about the infinity summation from between formula number 1, 2, 3, or 4? Which one talks about the sum to infinity?
Number 4.
It's number 4, exactly. They are giving you the answer even before, just by reading the statement here, before going to the question, they are giving you the answer. That here we need to use the formula for summation to infinity, of which you just have to find the first term and the common ratio, and you will be having the answer that they are looking for. Again, the other thing or the other indicator which tells you about the formula you're supposed to use is what we have up here. You can see we are no longer having the infinity term or the n, the capital letter N here, or the n. We are now having the infinity. That also guides you that what you are dealing with is infinity summation there. Okay, then now the very first thing which you need to do is for you to be able to identify the first term and the common ratio. I'm going to help you to do that with this first question. But on the second one, you should be able to do it by yourself. Let me show you how you identify the value of A and the value of R. This is how you do it. You are given the summation, and then now our summation is starting from n equal to 1. It means wherever we have n here, we're going to substitute 1, and then from there on the second term, we substitute 2, substitute 3, and so on, up to infinity. Let's start with substituting 1. If we substitute 1 here, we're going to have 3 to the power of 1 minus 1, which is equal to what?
3 to the power of 0.
And 3 to the power of 0 is what? It's 1.
It is 1.
Yeah, because any number to the power of 0 is 1. Yes, exactly. That's true. And then we go to the second term. The second term, we then substitute the 2, because this, it goes as 1, 2, 3, 4, 5, up to so on. We have substituted 1, now we need to substitute a 2. If we substitute a 2, it's going to be 1 minus 2, which is 3 to the power of -1. Therefore, 3 to the power of -1. I hope you remember that 3 to the power of -1 is the same as 1 over what?
Over 3.
Yes, exactly. So you need to write it in terms of a fraction to make it simple for you. But it's not a sin for you to write it as that. No one can mark you wrong because this is the same. Then we go to the next term where we have n replaced by 3 is 1 minus 3, which is -2. Therefore, 3 to the power of -2, it gives an answer of 1 over what? Over 9. Can any one of you tell me the next term that is coming after 1 over 9?
1 over 27.
Very true. We are going to have 1 over 27. But now we are having endless term in this case because we have sum to infinity. In other words, we are not going to have a last term. It's only on this sequence where you will not have the last term because it goes up to infinity. Remember, our task here is to get the value of A and the value of what? Of R. That is our task on this question, is to get the A and the R. But already, just by expanding, we have obtained the value of A. Can anyone of you tell me what will be the value of A in this case?
It will be 1.
Very true. It's going to be the first term or the first value we have from that series there. And then now, the only task we are left with here is to get the value of R, of which you must remember the formula for getting the value of R, which is common difference. So it's going to be T2 divided by T1. And T2 here is given as 1 over 3 divided by T1, which is given as 1. Therefore, the answer for R is 1 over 3. You may decide not to use T2 over T1. You can use T3 over T2 or T4 over T3. It's exactly the same thing. You will obtain the same answer of R equal to 1 over 3. Now, after obtaining these two values, you then go and substitute this formula we have identified already that is for answering this question. When you substitute, you will then obtain the summation to infinity equal to then the first term there, it's 1 divided by 1 minus the R in this case is 1 over 3. You are only left to simplify this, of which you can do using your calculator, but I don't prefer you to go straight to the calculator. Calculator is just for confirming that your mathematics is right in this case. So now you just simplify using your mathematics skills. So it's going to be 3 minus 1 divided by 2, of which is going to be 2 over 2, which is equal to 1. I believe you obtained the same answer, all of you. Can you use the calculator and check if the answer is 1?
No, the answer is 3 over 2.
Okay, where did I make a mistake? Let me check. So it's 3, yes, because here is 3. So it's 3 multiplied by 1, which is 3 minus 2, which is 2, and then divided by 3. Therefore, in that case, it's going to be 3 over 2. That's correct. I made a mistake there and put 2 instead of 3. It's supposed to be 3. These 3 we have it. So you just do simple manipulation right there, and then we deal with the fraction, we then obtain the final answer that we are looking for. And that is how you're supposed to attend to this question. Now, you can see this question covers the two aspects of the lesson we have covered today. So the infinity geometric series and the summation. So you should be able to treat the summation. In some cases, you may find that they treat you with this starting point. So you must be able to attend to the questions where they give a different value other than 1. They may decide to start from 0. So you must be aware of such situation where they are changing this value of n. Can I give you a question to try?
Yes, please.
Okay, let me do that just now. Okay, quickly do that question together with this other one I'm giving you just now. These are the questions I would like you to attend. I'm giving you let's say 7 minutes to attend to this question. Okay, this meeting is going to log off in 4 minutes time. So now when it logs off, make sure you use the same link to log in again. So it gives us sort of like a small break of about a minute, but make sure immediately when it logs off, you log in again using the same link. I think it's now about 3 minutes time, it's gonna log off. But in the meantime, this is the work I want you to do. When you are done, make sure you send your solution to my WhatsApp, or you can comment on this group so that we compare the answer you obtain with the ones I will do as correction on the board. Now it's your time to do that question. Come in. Hey. Oh, I have to. Oh, okay, thank you.